Afternoon to everybody. You're very welcome to today's event. My name is Orla Burke. I'm chair of the Electrical and Electronic Division of Engineers Ireland, and I'd like to warmly welcome you all today to the National Wiring Rules in Ireland, an illustrated guide to IS 10101 presentation by Brendan Dervan. I'd just like to take this opportunity to remind you all to keep an eye on the Engineers Ireland website for other upcoming events by the Electrical and Electronic Division and all of the other divisions in Engineers Ireland. So I'm just going to briefly introduce you to Brendan. I'd just like to ask you all, if you have any questions during the talk, please put them into the Q&A box at the bottom of your screen, and we'll take as many as we can at the end of the presentation. I know Brendan has received a few questions in advance, so he'll try to address them as he goes through his talk. So as I said, I'm delighted to welcome Brendan today. I'll just give you a quick info. Brendan is a chartered engineer, and I'm delighted that he is a fellow committee member on the Electrical and Electronic Division. He has over 40 years experience in all aspects of mechanical and electrical building services, including design, installation, commissioning and maintenance. After completing an electrical apprenticeship in 1982, he went on to study electrical engineering in DIT. He's worked in M&E consultancy at senior engineer director level since 1990. In 1999, he started his own M&E consultancy, Dervan Engineering Consultants, which merged with Cundall in 2016. His company provided M&E consultancy and project management services to a diverse range of clients in both the public and the private sectors. He's owner and director of BEST Training since 2019, so I'm sure many of you may have attended some of Brendan's courses in the past. For any of information on Brendan's other courses, you can visit besttraining.ie, and I'm sure Brendan will mention this in his presentation as well. So without further ado, over to you, Brendan. Thank you.
Thanks very much, Orla, and good afternoon, everybody, and welcome to this introduction to the new wiring rules. I have about 30 slides I'm going to present to you out of a total of approximately 650, I think, at this stage, total slides that I have. And this is actually a very important one, this introductory slide. On the left-hand side here, you can see the front cover of the new wiring rules. And you'll see the 3 books down the bottom there, IEC 60364, then the Senelec document, HD 60364. So that's the standard document throughout Europe that all member states are required to adapt in some shape or form. And then this is our own version, IS 10101, and it's the 5th edition of our wiring rules. The 4th edition, as you probably know, came out in 2008, and this is now replaced by this NSAI document. The book on the right, many of you will probably know, it's a guidebook, an illustrated guide to the wiring rules, which I produced. And thanks to COVID, I got working on it last year and launched that in October and November, and that is selling very well, I have to say, and it's been getting very good feedback on it. So, so I mentioned earlier on, this is a total of 650 slides I have produced, and I have spread over 3 different courses. I'm doing the Wiring Rules 1 course, WR1. At the moment, that's very, very popular, obviously, because of the transition period is up on the 31st of January. So as of from 1st of February, we're required to be designing to the new wiring rules. So that is quite popular, that course. And then the other 2 courses are deep dive on chapter 5, which kind of goes into the detailed look at chapter 5 in the wiring rules. And then WR3 is chapter 7 explored. Chapter 7 is the chapter that contains all the special locations. So that quite busy obviously on that at the moment. The other courses I run through Engineers Ireland, and they're available on you can see them on the Engineers Ireland website or my own website, www.besttraining.ie. Fundamentals of M&E consultancy, data centers, introduction to M&E services, looks at power and cooling in data centers and fire suppression and all that type of stuff. Very, very popular, big demand for that course. And then kind of sitting under that course, I do LV distribution, MV distribution, generators and UPS systems. So they're all fairly popular and they run regularly throughout the year with Engineers Ireland. So that's the guidebook. I mentioned that earlier on. I won't dwell too long on it. It gives really good insight, follows the standard, literally chapter by chapter. and it explains, it kind of translates into the language that we all use, electricians and engineers, and it just makes it kind of an easier read, but it follows it section by section, explains all the rules, and gives lots of diagrams and manufacturers' data sheets and things like that to explain what they're talking about. And you'll see some of those throughout the presentation today. So I've been presenting it since last November, so it's quite a popular course. You'll see some of the blue chip clients I have there, and obviously Engineers Ireland. I run it regularly through Engineers Ireland, and lots of people, different companies attend through that, which are not shown in this slide. These are just some of the people that have attended directly, including Recce, the inspectors in Recce, and lots of consultants and contractors. So let's get into the wiring rules itself then. So the structure is similar to before, but it is approximately twice the volume of the 4th edition. There are 8 chapters. They're called Chapter 0 to Chapter 7. And then there's a new Part 8, which deals with energy efficiency, which is a little bit of a departure from previous versions, because it is really nothing to do with wiring rules as such. It's dealing with electrical energy efficiency. So I'll run through the chapters very briefly here, and then we're going to look at them in a little bit more detail. So Chapter 0 is simply an outline and a normative references. So it just lists all the various ISEN norms that are referred to throughout the standard. Chapter 1 then deals with the scope and fundamentals. So it literally just talks about what the standard is all about and what it covers. Fundamentally, it's in a nutshell, the wiring rules is about protective measures for safety of persons, livestock, and property against the effects of the hazardous effects of electricity, such as electric shock, overheating, fires, overcurrent, over voltage disturbances, all that type of thing. That's what the wiring rules are all about. Chapter 2 then is simply definitions, about 20 pages of definitions that you don't need to read. You just know where to go if you want something, the formal definition of something. Chapter 3, very important chapter for designers, because it deals with general characteristics and how to assess them, things like maximum demand, the earthing arrangements, the type of supply you're going to connect to, etc., etc. Chapter 4 is all about protection for safety, and again, no harm in repeating it, safety to persons, livestock, and property. And it deals with, has 5 different sections dealing with protection against electric shock, thermal effects, including fire and all of that, overcurrent, voltage disturbances, and then means of isolation, etc. Chapter 5 then is called Selection and Erection of Electrical Equipment, but in the real world, what we call that is, if you like, specification and installation. So specification, normally done by the consultant, installation, normally done by the contractor, if you want to simplify it like that. That's what that chapter is all about, and it's closely related to Chapter 4. It looks at how you specify the equipment that is referred to in Chapter 4. And then obviously following on that, from that, you have now specified and installed the equipment. It has to be tested, and that is referred to as verification and certification, commonly referred to as testing and commissioning in other words, if you like. And then Chapter 7 is special locations, and we look at those later on, 20 special locations, including medical locations, campsites, PV panels, electric vehicle charging, all those specialist locations or installation types. And then Part 8 is this new annex on energy efficiency. So what we're going to focus today is on the changes, really. That's what most people want to know, what has changed. So I'm going to talk about, this is a busy slide, I know that. It's just to guide me through it here, and then we look at some of these changes later on. And I have got some questions in yesterday and today, and I'll try and address them as I can, but I'll be giving you my own personal opinion on them. Some of the questions I've been asked really require the opinion of the NSAI, but I can let you know my own personal view. Some of them I can't question because the information relates to things that happened before my time on NSAI. So we'll go through them. The first one is now that RCDs are now required on lighting circuits in domestic premises. So that's a big change, and we're going to look at that later on, how it affects the design of consumer units. Arc fault detection devices are now recommended. They're not mandatory, they're recommended in locations with particular risk, and it includes premises with sleeping accommodation, where the word premises means a domestic, you know, a normal house, or does it include apartment blocks? That's not clear, but it definitely is required in places, are recommended, nursing homes and communal buildings and the like. And that's really open up for discussion. That's really not 100% clear what way people are responding to that. There's now a risk assessment process for determining if surge protection devices are required. My own view is don't bother doing it, just put in the SPDs. It's the right thing to do. And if you don't put in SPDs, you've got to demonstrate now that you've carried out a risk assessment to show that they're not required. Risk mitigation methods, a huge section on voltage disturbances between transients and electromagnetic interference. It takes up a huge part of the standard. It was previously a half page in the 4th edition. It's now over 30 pages. Quite a lot of stuff in it. And in fact, when we get into chapter 5, it tells us there's an onus on the designer to provide documentation where requested to prove compliance with the EMC directive. Bit of a tall order. You're designing an electrical installation. You can't really test it fully for EMC compliance, but you certainly can follow the guidance in part 444. And if you do that, in my view, you're really doing the best you can to make sure the electrical installation is not going to cause interference elsewhere. 525, one of the questions that asked was the voltage drop tables are removed, which I think is a very, very bad move. I think they should have been left in, and hopefully they will be returned in future editions. They've replaced them now with a formula, which requires the designer to work from first principles, and it is a little bit confusing, I have to say. A big section here is now that cables must be rated to class DCA S2D2A2. Bit of a mouthful. In a nutshell, it just means PVC cables are no longer acceptable. So the old PVC, twin and earths that we use in domestic installations, NYMJ, and all other PVC-based cables cannot be used. So these cables are fundamentally an LSZH, so low smoke, zero halogen. A little bit more to that, and we'll touch off that later. Next one is type AC RCDs no longer recommended in new installations. So we'll touch off that later. So basically the recommend is that we use type A, and in some instances type F or type B, which are a very expensive alternative compared to a type A RCD. Surge protection devices, lots of new information in that section on how to select them, you know, how to be configured inside the panel and everything inside the distribution board. So lots of information on that. Isolation of premises. The 4th edition had some very, very prescriptive requirements in it, and they're now gone. And they've gone back to a simple statement about premises should have a means of isolation in an easily accessible location. Fundamentally, that's what's telling us. Much less prescriptive, and in my view, it's better. There is a lot of confusion out there about the difference between a main isolator in a premises and a firefighter switch, the red firefighter switch, which in my view is intended for turning off high voltage lighting, but a lot of installations it's been used now as the main to shunt trip the main breaker. So model certificates then are gone from chapter 6, which is testing and verification, etc. And then in chapter 7, there's a few new things like the electric vehicle charging, which was an addendum to the 4th edition, is now embedded in as part 722. Lots of changes in medical occasions, which is quite a specialist area. Then there's a new section on onshore units for inland navigation. This is, berthing marinas, etc., on the Shannon and that type of thing. And then Annex 8, energy efficiency, is a complete new section. So lots of interesting stuff in that. But if you're complying with Part L of the building regulations, and if you're doing BREEAM or LEED certification for a building, you'll find that an awful lot of these requirements are already met. It's a repeat of what we're doing under other energy assessment schemes, etc., and particularly Part L. Okay, so we look at chapter 4, very important chapter. It only has 5 parts, but each part, of course, has multiple sections, and then each section has multiple clauses. So it's quite complex to make your way through it. But just to note, the 5 main parts are 41 deals with electric shock. So probably not a whole lot of new stuff in 41. It covers automatic disconnection of the supply. in the traditional way we do it. RCD protection, SELV, reduce low voltage, like 110 volt distribution on construction sites. All of those measures are covered there, and lots of other stuff that was embedded up in the main narrative is now transferred to the annexes. So it's a complex enough section to follow. Then protection against thermal effects covers thermal effects like burns, but more importantly, fires from electrical installations. And it introduces a new recommended practice of installing AFDDs, arc fault detection devices. And you're going to be seeing more of these. They are recommended in places with sleeping accommodation and places where there's a risk of loss of cultural heritage, for example, a museum, an art gallery, something like that. They're recommended there, or buildings that have combustible materials stored, or the building itself is of combustible construction, like a timber structured house or thatched roof, something like that. You know, it's up to the designer to weigh up the risk where they're needed. But they're a new device, and basically the way the market is responding, they're combining the AFDD function in with an RCBO. So now our new protective devices they're going to be, if you like, in my language, I'm calling people, they're multifunction protective devices. They do overcurrent, earth fault, and arc fault, all in the 1, 2, or 3 module. So we look at some of those later. Protection against overcurrent, no real changes there to the best of my knowledge that I'm aware of. So that's just a standard thing about how to select a protective device, you know, fuse, circuit breaker, etc., and the relationship between that and the conductor cross-sectional area. So nothing really changed in that. The next section is massive changes on it. It's really, really big, 35 pages, I think, in total, versus a half page in the 4th edition. And then isolating and switching, again, I don't think there's any major change in that. So this is, I mentioned earlier on, the new risk assessment method for assessing whether you need SPDs or not. So the first thing I'll tell you about it, it lists a whole range of buildings that you definitely need SPDs in. For example, buildings where there's a risk of loss of life. So a hospital, okay, if you got a transient surge, could knock out a piece of life support equipment, that's clearly a risk of loss of life. Lots of other buildings, it gives you examples. Again, loss of cultural heritage, buildings, combustible materials, and all different sorts of examples it gives you where they are mandatory to put them in. There's no choice. It then goes on to say all other situations you must carry out a risk assessment. And it clearly says if you do not carry out the risk assessment, well, then you must put the SPDs in. So it gives you this formula here. I won't go through it. It takes a bit of detail to explain it, but it basically has 3 variables in it: an environmental factor, lightning flash density, and then another factor, this factor LP, which is basically determined from the ratio of the mix of overhead lines and underground lines, and between high voltage and low voltage. So you have to do a little bit of calculation there. The other 2 variables are very straightforward. You just pick them straight out of the wiring rules. And you carry out the calculation, and if the answer is less than 1,000, you must put in SPDs. If it's greater than 1,000, you do not need them. But what I advise everybody doing it on the course, this is purely an assessment of the risk assessment from a lightning strike. Most transient overvoltage damage in premises is caused by equipment within the premises and not lightning. So it's due to little transients that occur naturally in a building because of things switching on and off, photocopiers, your washing machine cutting in and out. They cause little transients to appear, and sometimes the transients can get to a magnitude that cause damage to sensitive electronic equipment. So in a nutshell, I would say don't really do this. Obviously, if you like the academic exercise, of course, go around, play around with it as I did, but I would be saying, you know, in a house, for example, an SPD is about 30 euros extra. Just put it in. It's the right thing to do. And it gives you a diagram like that explaining the ratio of all the different cables, overhead high voltage, underground high, and so on. And then you carry out an assessment as I did there, simply in Excel, bang it in, and you see I got an answer here of 733 for a rural network, and a rural network obviously has more overhead lines on it, so it's more susceptible to lightning strikes, and it has a lower environmental factor to start off with. So it's nearly always, I would imagine, if you did any rural network, you're going to find it's mandatory to put them in, essential. When you come to an urban network, because the factor is 850 to start off, the environmental factor, and most modern urban networks don't have a lot of overhead cables on them. The old ones sure do. The old residential areas all have overhead lines, but modern ones don't. It's all underground network. And you're always going to get a figure higher than 1,000. So if you want to do that and take the risk, but I would say put them in everywhere, because this is purely lightning, risk of lightning strike is all you're looking at here. So 444 deals with electromagnetic interference. It causes voltage disturbances and electromagnetic interference. And it gives lots of different diagrams and guidance, like the ones I've shown here. There's just 2 examples of things you should do to mitigate the risk of electromagnetic interference. So the diagram on the left is shown a dual-fed, double-ended substation arrangement, and showing you should only neutralize at 1 point. Obviously, if you neutralize at both points, your entire earthing system would be in parallel with the neutral conductor, and you would have leakage currents. You'd have neutral current returning through your earthing system. So that's why we don't do that. The one on the right is one that was kind of new to me. I never really thought about it, to be honest with you. And even though I've been specifying automatic transfer switches for years, it's shown again a main board fed with 2 transformers, an open coupling arrangement, but with a common neutral. And it shows you coming down to a critical load down here, fed through an ATS. Okay, so anyone who's not familiar with an ATS is automatic transfer switch, which just automatically transfers from the A supply to the B supply. And what they're telling us, you should only be using 4-pole. In the industry, it's quite common to specify 3-pole. And if you use 3-pole, here's the problem. When the neutral current comes back here, it can split up both ways and go back through the A path and go back through the B path. So only the A path is live. So that cable is out of balance because it's not carrying all its neutral current. And this one's definitely out of balance because it only has current flowing through the neutral conductor. So that stray current flowing through there is out of balance, and it causes a magnetic field to be set up around the cable. And that fluctuating magnetic field at 50 hertz can induce voltages into nearby signal cables and corrupt the data or do other damage. So that's really the thinking behind that. Whether it actually is that hazardous or not, I don't really know. It's a very specialized field, but I would be inclined to say you should be following the guidance. If it's recommended use 4-pole, you should be really using them. And particularly if there is an EMI issue later on, you can't really sign off and say you've complied with the wiring rules if you've gone off and used a 3-pole. Okay, a little bit more, it talks about segregation of circuits. So what you see in the diagrams is a similar diagram in the wiring rules. It's just common good practice that we all follow as designers or contractors. We segregate our LV circuits from our ELV. So that's mandatory because ELV circuits is usually safety extra low voltage, and it's a requirement in part 41 to segregate the 2 types of services anyway. And then when you read the various standards, IS3217 and IS3218, it talks about segregating fire alarm and central battery emergency lighting circuits from other circuits. And that applies to all life safety circuits, basically. And then good practice, but not essential, ICT cables should really be on their own cable management system. Lots of people mix them with the other ELV, but that's really kind of what I'd call good practice. And they're recommending that in this section, again, with a view to mitigating EMI. And that's chapter 4 in a nutshell. And we've only an hour, so I can only spend very little time talking about it. Chapter 5 has 6 main sections in it, and I'm just going to spend time talking about it because people get lost in it. It really is hard to find your way around it. But if you can kind of keep these 6 main parts of the chapter in your mind, it'll help you get through it. Just as in part 4, we just looked at, first part is electric shock, then thermal effects, then overcurrent, voltage disturbances, and isolation. It's easy enough to remember. I know I'm rhyming it off every day. I'm doing this every week, but it does, if you get your head around what's in each section, you'll find stuff much more easily. So this is broken into 6 sections, and the first one is part 51, deals with common rules. So things like color coding of cables, identification. It deals with PE currents, which is protective earth currents. These are normal currents in a healthy circuit that are flowing through the earth wire, and it actually to make an assessment of them to make sure you're not going to get nuisance tripping. It looks at external influences, mutual influences. So external influences like you know, water ingress into electrical equipment, dust, and so on, IP ratings, all of that stuff is covered in. Cables under floorboards, cables embedded in walls, all that type of stuff is covered in here. In fact, some of what I'm talking about is actually covered in Part 52 as well. So Part 52 is wiring systems. So it covers the different types of wiring systems, cable management, current carrying capacity of cables, the approach for sizing the cable, some standard cross-sectional areas of conductors. Then goes into voltage drop, which, you know, they've removed the voltage drop tables. I mentioned that earlier on and replaced it with a formula, very complex formula. Connections, spread of fire. So in this spread of fire section, they talk about this new DCA cable, the fire performance of the cable to comply with the construction product regulations, CPR regulations. And basically the days of specifying PVC are gone. And we look at some of these things now in a few minutes. 53 then is switchgear. So if you look at chapter 53 and read down through there, you'll find it follows almost section by section what we just discussed in chapter 4. Yeah. So 531 looks at devices for protection against electric shock. 532, devices for protection against fire, such as 300 milliamp RCDs, arc fault detection devices, and so on. 533 deals with overcurrent devices, you know, direct follow on from part 43. 534, overvoltage devices, undervoltage device, and so on. So follows very closely chapter 4. 54 deals with earthing, and by and large it's unchanged. It's much the same as before. 55, there's a real bugbear of mine. It's you know, it's everything else. You know, so this is wiring, switchgear, earthing, and then everything else just dumped into one section here, into section 55. And what I don't like about it is there's no shortage of numbers. You know, we've 57, 58, and so on. Generators is such a big, complex area. It should have been taken completely out and put into its own section. That's my view. Because when it talks about generators, most of us in building services sector thinks of, oh, generators, they're talking about diesel powered alternators. And no, that's only one little part of what they're talking about. It covers micro generators, micro turbines, PV systems, UPS systems, rotary converters, all that type of thing is covered on it. And then there's other parts like motors, transformers and stuff. Very, very little information in it. It doesn't tell you a whole lot really. Plugs and sockets, lots of useful information in there, and some guidance in the associated appendices. Electrical appliances, you know, a mixed bag of stuff in that. Auxiliary circuits kind of relates to stuff inside motor control centers. You know, do you use low voltage ELV, or should I use mains voltage, and so on? Should I use AC or DC for the auxiliary circuits, and give some good guidance on that. 559 then deals with luminaires, so it goes through all the various standards to do with luminaires and then some wiring methods. Unfortunately, it doesn't really address a lot of the modern approaches we take to wiring lighting using, you know, DALI, KNX, and all these technologies we now use, and lighting control modules, LCMs with multiple outlets in the one box, etc. But anyway, and then safety services, a very important chapter. Safety services is what we would have called in the past firefighter services. So firefighters, lifts, evacuation lifts, smoke fans, all those types of things are covered in here. It also talks about emergency lighting and fire alarm and the essential power supplies to them. But really, I don't feel it should be there, because, you know, they're covered under standards, and the backup power supply is a battery within the system itself. So that's what's covered in that. So the first thing I'm going to look at is voltage drop, and somebody actually raised the query yesterday, and it's been from the day I got the standard. It was my first comment back to the NSI. Why have you taken out the tables? You know, that's what we all grew up using, and they've given us a very complicated formula here, okay? And it works from first principles. It looks at the resistivity of copper and the reactance of a typical low voltage cable. And you have to know your cosine, your power factor, and use the cosine, and then get the sine of the angle. Blah, blah, blah. It's very complicated. It does work. You put it into Excel, but be very careful when you're using it for three-phase voltage drop calculations. Your answer comes out in phase voltage, okay? So you need to convert it back. You need to multiply back. And there's a bit of argument, a big academic discussion about that at the moment. whether this factor here, B, whether that factor should be 1, as they tell you here in the wiring rules, or whether it should be 1.73. In my view, it should have been left at 1.73, and a lot of people agree with me. It would have avoided an awful lot of confusion. But just beware, if you do, which I've done and many people have done, I've banged in some figures here, put into a spreadsheet, and I compared the results with the previous tables, and you'll find they're very, very close for single phase, but they're way off for 3-phase. And the reason they're off is because this factor says 1 instead of 1.73. Of course, if you multiply it back by 1.73, your answer, you'll bring it back to close to the values in the previous tables. So just to relieve anyone that's going to start worrying about that and say, oh God, how am I going to adapt my spreadsheet to do that? It tells you, you may calculate the voltage drop using this formula. It doesn't say you cannot use the tables anymore. Of course you can use the tables. They're IEC tables, and lots of other countries have maintained them in their wiring rules. So you can still use the old wiring if you so wish. And if I was still working as a designer, that's what I'd be doing. I certainly wouldn't be using this. Another important part in chapter 7 of chapter 5 is minimizing the spread of fire. So I mentioned earlier on the CPRs. These are the construction product regulations, and they now have brought out a classification system for designating the fire performance of cables. So in Ireland, we've chosen that the minimum performance now is DCA S2D2. In other words, you need to do better than that. That's the absolute minimum that will be accepted now. So for example, a cable worse than that would be an ECA, which would be a kind of a PVC cable. They're no longer acceptable. So it's basically in the realm of, I suppose, LSF stroke LSZH type cables. So let's look at what it means. There's, DCA is the first part of the reference. The D just stands for the fire performance. So A is a non-combustible product, if you like, and F is a product that has no what's called rateable fire performance. And B, C, and D, it gets better. E is like PVC, D is kind of like LSZH type cables, C is higher performing LSZH cables. And to be honest with you, I don't know what B and A are like. A is effectively non-combustible, so I can't find any data on it, but I'd imagine something like bare MICC, which is a non-combustible cable, would fall into that category. But other than that, I'm not really sure if there are any cables rated for, are rated ACA. The little CA in the subtext beside it just simply means cable. That's all that means. And then the 3 other references are S2D2A2. So S stands for smoke, D stands for droplets, and A stands for acidity. So you're looking at, the hazardous nature of the cable when it's burning, when it's attacked by fire, what happens. So we're looking for obviously minimal smoke, minimal acid, and minimal drops from the cable. So S2D2A2 is the particular specification we went for. For example, S1 is better than S2, D1 is better than D2, and A1 is obviously better than A2 as well. So a lot of people are now calling their specs, calling for C cables to meet CCA classification. And there's no great difficulty in getting these cables. People thought at the start, oh God, this is something unique to Ireland. It's not, we're only 1% of the population of Europe, and these wiring rules, everyone's basically specifying similar cables throughout Europe. And I did as an exercise when I joined. I should have mentioned at the start, actually, I represent Engineers Ireland on the NSAI TC2 committee, which looks at developing the wiring rules. And at the moment, we're dealing with lots of queries from the industry and that type of thing. So I represent Engineers Ireland on that. And one of the first things I did when I joined the committee, I started exploring and said, look, well, these 10 cables you see here represent probably about 90% of the cables that we use in electrical installations. So from domestic twin and air type cables, NYMJ and so on, SWA and fire survival signal cables, then fire survival power cables, and so on and so forth. I put these together in a spreadsheet and sent them off to one of the manufacturers in the UK and said, can you confirm if these cables are available to meet our new minimum requirement, DCA S2D2A2? And not only did he come back and answer me, he came back with the product reference codes the next day. So I was greatly relieved to hear that, that not only were they available, the manufacturers had to tell me the product specification code. So when I reported that back to NSA, I think it relieved a lot of people to know that there's no great mystery about it. It's just really an LSZH classification that has to go under a very, very specific tests. And when it undergoes those tests, the manufacturer tends to designate or rate it as a DCA cable or a CCA cable, depending what it is. Now, next big change, and I'll dwell on this one because it's creating lots of queries, and some gentleman sent in a query yesterday, and I unfortunately couldn't commit myself to answering all of his queries, but I'll address some of them now. First thing about consumer units, in part 42, which deals with spread of fire, they said that a consumer unit should be manufactured from metal, non-combustible material, or materials complying with a particular EN reference, which I can't remember off the top of my head, EN 67575, I think it is. Basically, it's a standard that deals with flammability tests, glow wire tests for products. So basically what it's saying, you either use metal, which in my view is the best option. And I regretted when I went on some of the early talks on the new wiring rules back almost 3 years ago now by Charles Dunn and others. They were talking that was going to come in, and I said, hallelujah, we got rid of those awful plastic consumer units because they're really difficult to work with. They're too small. And I've been involved and I've done reports on at least one case in my career where an apartment went on fire. The consumer went on fire in the apartment and ended up like a ball of carbon lining the floor of the apartment. And so thankfully nobody was injured as a result. And I was down to a loose connection in the consumer unit. Had that been a metal consumer unit secured to the wall, I don't think it would have collapsed off the wall and probably would have contained the fire a little bit better. So that's one of the things that's dealt with. It says metal or non-metallic materials complying with a specific standard for the glow wire test for the material. The other standard, of course, for all consumer units is they must comply with EN 61439, which is the switchgear standard. And part 3 of that standard specifically deals with what they call it, distribution boards for unskilled people, if you like. So in other words, consumer units in houses where the people resetting the breakers, etc., are non-trained electricians, etc. And they have very specific requirements. So that's one of the changes, okay? Regrettably, it didn't end up as metal. If I was there now, I'd be hammering down the table and insisting that we go metal. I think it's the right way to go personally, and deeper, give us more space in the consumer unit. So some of the other changes that have occurred, double pole switching now required in the consumer unit. And obviously, if you're in a normal domestic situation and the consumer unit is right beside the meter cabinet, this has to be a circuit breaker. So it's a single pole plus neutral circuit breaker. SPDs, I mentioned earlier on, it tells you that they're not really mandatory, but you have to go off and do a risk assessment, as we explained before. I can't see anybody bothering their Barney doing that. I can just see most people saying just put it in. It's another 30 euros added in. Now the rest of the consumer unit here, some might say, well, that's squeaky clean, very nice consumer, and it is consumer unit. And if I was a designer, this is what I'd be telling my client, this is the right way to go. So what I'm showing here is they're effectively RCBOs, but if you can see the text there, I have AFDD RCBO. So what I'm suggesting is that we move along, even though it's only a recommendation, I think we should move towards arc fault detection devices in consumer units. It's there to protect people's lives. This might cost you 1,500 euros versus, 120 euros for a consumer unit at the moment, probably 1,500, maybe 2,000 euros. People have no problem going out and spending 1,000 euros on their, flat screen TV or whatever else in the house. It's a small price to pay for something that's dealing with life safety and protecting people's lives. And in my view, this is the way we should go going forward. So, so we've the surge protection device, and then we simply have whatever it is there, about 11 combined RCBO AFDDs. And it's very simple then. Each circuit just comes in, it individually terminates onto its own pair of terminals, and you just bring up your earth wires onto the earth bars here. It's very simple, nothing complex about it. That's one approach to it. You might argue and say, well, domestic premise, a private domestic home is not does not fall within the remit of a premises. It's not very well defined what a premises is. A domestic, or what way is it? premises with sleeping accommodation. That's what it's described as. So I must say, if premises with sleeping accommodation, it's recommended. So I'd say premises with sleeping accommodation is student accommodation. I would put apartment blocks. This is my own personal view. This is not NSAI's view. This is my own personal view. Nursing homes, of course. Hospitals are exempt from it. As in Part 7, hospitals do not have to have AFDDs in Group 2, Group 1 and Group 2 areas. So I would consider all those buildings other than your normal private dwelling. I would consider all of the situations to be a premises, an apartment block premises, student accommodation premises. And I would say we should be driving the message home. We've got to put AFDDs in. It's the right way to do it. And if that's the case, that's a very simple approach. In the normal domestic situation, the board would look very, very similar, but they wouldn't be AFDDs. They'd be just 2-module RCBOs. But you can see how squeaky clean that is. But if you go to the next slide, look how complex that is. And this is where we're going. This is where the industry is responding to the new requirement. The new requirement is that all the lighting circuits in a house now must be protected by an RCD. Okay, so you can't put both lighting circuits obviously on a one RCD, or a trip on a faulty toaster, faulty kettle or something could knock everything out in your house, all your sockets and all your lights. That would not be on. It wouldn't be compliant with chapter 3, which talks about divisions of circuits for safety, etc. So as a minimum, you've got to have 2 RCCBs in the board. And typically the way you do it, maybe the ground floor sockets and the upstairs lights would be on the same RCCB, so that if the ground floor sockets, if the ground floor lights stripped out, you could plug in your ground floor sockets will still be okay. So you just plug in a few standard lamps or whatever, and vice versa upstairs. If the lights go upstairs, you can plug in a few table lamps because the sockets are still running. So if we look through this kind of maybe a bit of an exaggerated approach, but this is the way that the modern house is going to go. So double pole switch again, surge protection device, dual RCCBs, several MCBs down, lights upstairs, let's say, and a few sockets downstairs, one of the kitchen circuits, and the opposite. So the other half of the sockets are here. And then we have to have some dedicated RCBO. So what are they for? Item 8, electric shower has to be on its own RCD. You cannot put that on the sockets RCCB. So it really needs to be an RCBO, okay, on its own. Then you need one for your EV charger, and that may be a type A or a type B, depending on the charging arrangements you go for. And then if you have a PV system, and of course we're trying to, in Ireland, achieve 70% of our electricity from renewables by 2030, a tall order, and we're making great inroads with wind, but we need to do a lot more. So we need to have a lot more PV panels on all the new houses and the existing housing stock. So if you put a PV system on, it's deemed to be a micro generator, and that has to connect in via its own dedicated RCBO. So that's another RCBO. So what I'm showing here is not really too far off the mark of the way the modern consumer unit is going to look. In my view, putting that inside a plastic box with a push-on cover is nonsense. Move away from it. This should be a metal box, 100 mil deep, plenty of space in it to work with it. And we shouldn't be going for that solution. We should be going for this one. Okay, either RCBOs or combined AFDD RCBOs. And I keep hammering that message home, and people keep saying, "Oh, developers won't go for it." Developers should be going for it. This is life safety we're talking about here. And some other changes. This is a brand new slide, so it hasn't appeared in any of my presentations yet. Well, it did actually one yesterday. So it's again showing some other changes to do with consumer units. The height has changed. It's clarified now as 2150 to the top of the highest protective device, the top row of the protective devices. I think the previous one, it was 2250 to the top of the consumer unit. So it's 2150 to the top of things. That just doesn't apply to consumer units. It applies to other switchgear. Meter cabinets, some of the things that's going to happen if the distance from the meter cabinet to the consumer unit exceeds 3 meters, you should be putting a breaker back here. You should have a circuit breaker here protecting this cable. And if you do put the circuit breaker here, well, then this becomes a double pole switch in your consumer unit. A lot of people are not following that and not fully realize that is the requirement. Within the meter cabinet, DSB obviously uses smart meters now, and some of them have the isolation facility built into them, into the meter. Some of them, it's a separate meter. And again, I think the ESB are changing the meter design now, and you may find we're going back to the separate isolator. The other thing I'm showing here is under discussion at the moment is, again, the rollout of, we're trying to move towards electric vehicles. So they are going to allow the electric vehicle charger to be fed directly from the meter cabinet, which means now you're going to have to fit a main distribution board effectively in the meter cabinet with an RCBO feeding your charger and a circuit breaker then feeding the board. That's the way it's going to go. So there's some of the things that are happening. These are not all necessarily IS 10101 requirements, but they're all tied in. Most of what you're looking at here are IS 101 requirements. I mentioned earlier on as well, type AC RCDs are no longer recommended. They again, in my view, they should be really just taken out and just say stop using them and just use type A. It's far better. So basically, type A RCDs are you know, they go back to the early generation of ELCBs when they first developed back in the 70s, and they were only designed for detecting sinusoidal earth leakage currents. But of course, the world we live in now, almost everything we plug in now, if it has an illuminated display on it, a digital display or whatever on it, that means you have DC power within the device. And once you convert AC to DC, you get DC leakage currents, either pulsating or direct DC leakage currents, and they have an impact on the operation of the traditional type of RCD. So they're really not suitable where you have a lot of leakage current. So for that reason, many moons ago, you know, it's not a new thing. I changed my spec back in 2003 or 4 and moved over to type A. And they are resistant to DC up to 6 milliamps. Okay, if you know you're going to have more than 6 milliamps of DC leakage current, it will affect the operation of it. So you should be using maybe a type F or a type B. So that's all covered in the new wiring rules. So it refers to all 4, but it's kind of saying as a minimum, you really should be using type A now. Arc fault detection devices. So I've shown this image here. I have no idea is that a fire due to arc fault, but it gets the message home. This is what happens with loose connections and breakdown in insulation. Over time, you get a generation of heat due to the loose connection or the breakdown in insulation. Starts little small currents start to leak, or whatever, or current trying to jump across an air gap due to a loose connection. It causes ionization of the air, which results in heat buildup, which results in the insulation starting to burn, develops into carbon, then more tracking, etc. And it's just a vicious cycle, and eventually builds up and starts a fire. So for that reason, they're recommending now AFDDs be used in certain installation where there's a risk of loss of life and so on, that we mentioned earlier in chapter 4. So I personally think we should be moving in the same way we stopped using screw-in fuses back in the late 70s, and we used to MCBs, and then we start using ELCBs, and then we moved to RCBOs. Like, arc fault detection devices are going to do for fire prevention what earth leakage circuit breakers or RCDs did for protection of electric shock. Same thing, it's advancement in the technology. We should embrace it, and it's protecting lives, and let's go for it. And that's what they look like. That's the ABB one. You know, all the major manufacturers, Schneider have them, Eaton, Garrow, they're all doing them, and they've all different versions of them. Most of them appear to be 3 module, but in the UK, there's a lot of single module versions, because obviously a lot of boards where you want to change them, you won't necessarily have the space. So there are single module versions out there, but you can see there's 2 buttons on it, orange and white. So the orange button there is the test button for the arc fault function. White button is the earth leakage function. And to the best of my knowledge, when it trips out, the little LED here it's a phase change LED. So it'll tell you whether it's an arc fault or an earth leakage fault. And if it's neither of those, then it's an overcurrent. So very clever piece of technology. Different manufacturers have different ones out there. And I need to do a little bit more research on it myself. I'd love to get them a bit of hands-on, play around with them and see what they look like. So that's what they do. Basically what they do is they have a clever piece of electronics in here that monitors the waveform. And when you have abnormal arcs or dangerous arcs on the installation due to loose connections or breakdown in insulation, I should say, it causes little spikes and what would you call it? Like a signature, I think is the term they use. It sets up the signature pattern, if you like, on the wave, on the sine wave. And these devices are specifically tuned in to identify that. And it can differentiate between normal arcs, because we've normal arcs every day of the week. Every time you turn on a light or something in your house, or the washing machine goes from spin program to drum program, whatever it is, you get arcing across contacts, and they're normal arcs. Or, you know, motors, the vacuum cleaner has a series motor, you know, brushes. So all those little arcs are normal, and they ignore those, but will trip out on a dangerous arc as such. So, and then the next area, of course, we mentioned that there's a huge growth in the volume of in part 44 talks about transient overvoltage protection, and basically how we protect against transient overvoltage. We use surge protection devices. So been around a long time. In the past, we specified these as part of the lightning protection system, but they're now clearly embedded in the wiring rules, telling us in part chapter 44, we should be assessing the risk of transient overvoltage and putting these in. In fact, they're mandatory in most locations. So that's what they look like. And there's type 1, 2, and 3, as you probably know. So type 1 is used on all buildings where you have lightning protection, or where there's a risk of a direct lightning strike. For example, if you had overhead cables, you know, bracketed straight onto the wall of your premises, and then a cable coming down, that would be a direct risk as well. If you have lightning conductors on your building, that's a direct risk, because the lightning strikes, hits the ground and goes up through the earthing system, back through your earthing system, and tries to spread its way through your installation and burn everything in its pathway. Literally sets up very, very high voltages, and will, when I say burn, it'll burn out, you know, things like integrated circuits in your television or whatever. So that's why we use these systems. So type 1, if you have lightning protection. Otherwise, your main SPD is a type 2, and then you use either type 2, combined type 2, type 3 downstream, etc. And ultimately what you're trying to do is protect sensitive equipment here, like your PC, TV, etc., against voltages. These are only designed to withstand impulses up to 1.5 kV. So what you're trying to do is clip the voltage and make sure you don't get voltages appearing of that level throughout your installation. And they are type 1, type 2, and type 3. That's them there. And you've a little description on them there, the type of technology to use, etc. And then chapter 6 then is all about verification and certification, or test. Just like to use the word testing, which it rolls off the tongue more easily for me. Testing and commissioning, we often call it. So there's a whole raft of tests you have to carry out before energization and after energization. For example, before energization, you've got to check the continuity of certain conductors, especially the earth conductor. Make sure you have an earth connected to every location. That's very, very important. Ring circuits, you've got to check for continuity there. You've got to check for polarity before energization. So go around and make sure, you know, all sockets are correctly wired, etc. What else do you do? Insulation resistance has to be done before you verify. So that's you know, you put a test it initially at 250 volt and then 500 volt, and make sure there are no breakdown in insulation. For example, a cable could have got damaged during the installation. And then post connection, you've got to check things like the operation of RCDs to make sure they function correctly, and most importantly, of course, check your earth loop impedance to ensure that the impedance is low enough to achieve the disconnection times specified in chapter 4, which deals with protection against electric shock. And then periodic verification, really a funny area. It kind of tells us, you know, every year visual inspection of buildings, and every somewhere between 3 years and 5 years, depending on the nature of the building, we should be carrying out periodic verification, which is really telling us we should be going back and repeating the tests that we've carried here at the initial verification. In reality, nobody does that, and it's probably an area that does need to be addressed going forward. And there is reference to recommended doing a periodic verification when a house is changing hands. And I personally think someone again asked the question, I think in the recent days before this seminar, and I would agree. I think it's highly recommend that before a house changes hand, the same we deal with BER certs, etc., you should get a mandatory PIC, periodic inspection, a PIR they call it, a periodic inspection report. It's the right time to do it.
Brendan, just to let you know, it's just coming up to 5 to 2.
Okay, thanks very much, Orla. I'm nearly there. I think, yeah, we're nearly there. We'll finish in 3 minutes now, hopefully. Risks, special locations. This chapter 7 deals with special locations or installations. And the reason they're in here is because there's a higher risk of electric shock or a higher risk of loss of life. For example, in a hospital, an interruption of the power could cause someone to die, like on life support or something like that. So in most cases, the risks are dealt with increased use of RCDs, increased use of SELV. You'll find there's lots of references in, for example, marinas, campsites, industrial locations, etc., to IEC 60309 sockets, or commando sockets, as we call them in the industry. And of course, then in healthcare, medical locations, there's a whole raft of special requirements in there, such as isolated power supply systems and all of that. So they're just some of the locations. I'm not going to go through them all. Rooms with a bath or shower. We all know that most buildings have nowadays, even an office block has shower rooms for people to change, etc. Swimming pools, special requirements, saunas, construction sites, 110 volt distribution, agricultural premises, susceptibility of livestock to electric shock is very, very high. So we've got to protect them. Lots of bonding and earthing requirements, etc. Caravan parks, marinas, very similar. RCD, trailing leads, commando sockets, blah, blah, blah. Medical locations, it's a whole really specialist area on its own. Exhibitions, dentists, then PV systems, a lot of new rules in there and important stuff in there. External lighting, much the same as before. ELV lighting, the same. Mobile units, if you're involved in that. Caravans. Electric vehicles, very, very important because we're putting electric vehicle charging points in everywhere now. So that's a really important one to be aware of. Inland navigation is very similar again to marinas. And then fairgrounds, circuses, all that type of thing. And then finally, I won't go into this one. Chapter 8 is on energy efficiency, and it is 3 individual annexes. And the first one is like a thesis on electrical energy efficiency, lots of interesting information that you probably already know, but it's really nothing to do with life safety. It's informative rather than normative. It means you don't have to comply with it or anything. And then in the other 2 annexes, it gives some worked examples of what it spoke about in the previous annex. And that's basically it. So folks, thanks very much for your attention.